Welcome to Physics 142. We're starting a new section which is about the diffraction of waves. When a wave passes through a narrow aperture, as you'll see in this demonstration in a moment, it actually, when it goes through, can bend around the corners of the aperture. What you'll see in a moment is a wave starting on the right-hand side of the screen, moving to the left, passing through a narrow aperture. So I'll stop it for a moment. You can see the waves starting in the right, moving to the left, pass through the aperture, and they look like circular waves once they pass through, because the wave amplitude has bent around the corners of the aperture. If these waves instead had simply been particles, then they would either go through the aperture or not, and the ones that go through would simply proceed in straight line paths. But these waves behave differently. Watch the rest of the animation. So what's going on here? Is there some way that we can analyze this in more detail? Let's look at the clip one more time. It turns out that these waves not only pass through the aperture and bend around the corners of it, but when they're viewed on a viewing screen, there actually will be a bright and dark series of fringes, very similar to the ones that we see when waves go through two slits. So what's going on there? Can we understand that in a little more mathematical detail? Let's do that right now. Okay, for a little bit more quantitative understanding of this phenomenon of diffraction, we're going to look at an incoming wave encountering an aperture or a slit of width A. And we're going to look at the wave along the direction theta measured from the horizontal to see what happens on a viewing screen. And what we'll do to start off is break the slit down in two halves, an upper half and a lower half. And we'll look at the amplitudes of the waves that move from the upper half and the lower half and how those interfere with one another. So let's look at the path difference between the waves that travel path 1 and 3. The waves that start at the very bottom of the slit, at the bottom of the bottom half, and then path 3 that start at the bottom of the top half. And those two waves have a path difference that you can see here is given by a over 2 sine theta, because a over 2 is half the aperture, which happens to be the hypotenuse of this triangle. The angle theta, measured from the horizontal, is the same as the angle in the triangle, and therefore the side opposite it is a over 2 sine theta. So the path difference is a over 2 sine theta, and that's also the path difference for paths 2 and 4. And so every trajectory from the bottom half of the slit can be matched up with another one in the top half that's offset by a over 2. So all of them together will have the same path difference. So completely, the whole bottom half and the whole top half will have exactly the same path difference. And we know what the criterion is for constructive and destructive interference. And we're going to focus here on destructive interference. So for the path difference, the a over 2 sine theta, to cause destructive interference, we need it to be a half integer multiple of the wavelength. We're assuming here monochromatic light, so one single wavelength. And a way that we can write down a half integer multiple of the wavelength is to write it as m plus a half times lambda, where m is equal to 0, 1, 2, and so on. That causes destructive interference between the top and bottom half. Therefore, if I just multiply both sides of this equation by 2, I get a sine theta is 2m plus 1 times lambda. So if m is 0, that gives us lambda. If m is 1, we get 3 lambda. If m is 2, it gives us 5 lambda, and so on. It gives us all the odd integer multiples of the wavelength. But, see, we don't just have to divide the slit in halves. We could now divide each half in half, so that we would now be dividing the slit into quarters. And we could play the same game of matching up the different paths and determining their path difference. And if we divide the slit up into quarters, we'd get the same kind of result, except it would be a over 4 sine theta. And then when we set that equal to a half integer multiple of the wavelength, we would get different values for a sine theta, but still those that cause destructive interference. And then we could also divide the slit up into eighths and sixteenths and so on. And if we keep doing that, we would accumulate more and more values on the right-hand side of this equation for destructive interference. And it turns out that if we did that, we would always get any integer multiple of the wavelength. So not just the odd integer multiples, but by dividing the slit into smaller and smaller pieces, we would eventually get all of the integer multiples. So this is the master equation for destructive interference due to diffraction. And if this bothers you a little bit, then that's okay. It probably should, because before, when we were dealing with interference, we learned how waves going through two different slits could interfere with one another to cause constructive and destructive interference. And it seems a little odd that for just a single slit we should see something similar. And yet we see the answer here, or at least the explanation, that light going through different parts of the slit can interfere, not light, but waves. Waves going through different parts of the slit can interfere with waves going through other parts of the slit. And so that's how we can get an interference pattern even when we're just looking at waves going through a single slit. Oh, one thing about this equation, a sine theta equals n lambda. N in this equation cannot be 0 for destructive interference, because if n were 0, that would be theta equals 0, and we will always see in the straight ahead direction where theta equals 0 constructive interference, because at that point the waves that come from different parts of the slit, the top and the bottom, are traveling the same distance to get there. And so this equation has to be understood as applying only to non-zero integer values of n. Well, if we consider the intensity pattern for the single slit, you'll see it here in the blue graph. It shows a maximum intensity at exactly theta equals 0. It makes sense that that should be the brightest spot. And then we'll see the locations of these different minima as we go upwards and then downwards from the central maximum. So n equals 1, n equals 2, and so on. Those are the locations of minimum intensity for the waves. And we can have negative values for these because those would correspond to the minima below the center of the screen. You'll see that the next maximum is a little bit fainter than the central maximum, and so on and so forth. So the intensity pattern from a single slit pattern decays pretty quickly, so we're only going to see a few of the bright fringes before the intensity gets too low for the eye to detect. So if a sine theta is n lambda, and we solve for sine theta, we get lambda over a for the first interference minimum, or diffraction minimum. And normally, if L is a large distance, if the distance between the slit and the screen is a large distance, then sine theta is approximately equal to theta. So theta is approximately lambda over a, as indicated here. And this is the correct answer for a rectangular slit. But we'll have occasion to look at some problems where instead of a rectangular slit, we actually have a circular slit. And in that case, the geometry is just a little bit different. And so when we do the math, it turns out for a circular aperture that the angles that tell us where the minimum intensity for the waves happens to be is given by 1.22 lambda over d, where d is the diameter of the circular aperture. We can also easily figure out an approximate requirement to observe diffraction. If we're going to observe it somewhere on the screen, of course, then theta has to be less than 90 degrees, which means the sine of theta has to be less than 1. Therefore, if sine of theta is lambda over a has to be less than or equal to 1, which means that lambda has to be less than a. If lambda is greater than a, we simply will not observe any of the minima on the screen. So it's important for the wavelength to be less than the aperture size. However, if you go back to the equation for sine theta up above, we also don't want lambda to be too small compared to a, because if it's too small, then the angle at which you would see the first minimum will be very small. And if it's very, very small, then all of these different minima and maxima will just sort of bleed together, and we won't notice them. So we want the wavelength to be less than a, but not too much less than a, in order to observe this diffraction effect. Well, now let's talk for just a second about what happens when we put the single slit and double slit patterns together. This can happen because in the double slit experiment, each of the two slits cannot be completely narrow. It can't be infinitesimally narrow. There's going to be some width to each of these slits. And so it turns out that what happens when we shine light or when we use waves that go through two slits like this, we will see on the viewing screen a combination of the single slit and the double slit interference patterns. So what you see first of all, and it says here red, although on my screen it looks a little bit more like purple, you see this rapid oscillation of intensity with a central peak at the center and then nearby peaks. Those correspond to the interference pattern of the double slit. But what's different now is that since each one of the two slits has its own diffraction effect, we see superimposed on the double slit pattern the single slit pattern with a central peak and then going down to a minimum on either side of the center line and then going back up to another maximum. So you can think of this as the two slit pattern modulated by the diffraction pattern of the single slit. The two are multiplied together. So we can use the condition for the maximum and minimum for the double slit pattern to find out where these locations are. But then we can also find locations where there's going to be a minimum in wave intensity using the single slit equation right here. And when the single slit pattern and the double slit pattern overlap at the same point, then we will see that some or one of the double slit fringes may be missing. And so we can easily figure out the condition for that. Let's say that the nth minimum for the single slit, which is given by this equation here, occurs at the same angle, theta 1, as the nth maximum of the double slit. So if these two angles, theta 1 and theta 2, are the same, then where there would have been a maximum for the double slit pattern, there won't be, because it will occur at the same spot as the minimum for the single slit pattern. In other words, this nth fringe will be missing. And we can easily find a relationship for that if we solve those two equations for the sine of the angle and then set the angles equal. We'll see that n lambda over a is equal to m lambda over d, and if we solve for m, we'll see that the fringe with index m will be missing. So taking d, dividing by a, and multiplying by the n value for the minimum in the single slit pattern, that will tell us which one of the double slit fringes will be missing. And we'll be doing some problems to illustrate this and to illustrate all these principles in class. So hopefully this has been a clear introduction to the phenomenon of diffraction and how it relates to interference that we've already studied. I'll see you in class.